Discover how massive aircraft and high-tech machines unite in the thrilling process of crafting powerful, precision-made tires. At Fukuoka Airport, RJFF/FUK, All Nippon Airways Flight JA756A, a Boeing 777-300, begins its takeoff procedure. After receiving clearance from air traffic control, the aircraft taxis onto the runway. The pilots align the aircraft precisely before initiating the takeoff roll. Engines spool up to full power, producing a strong thrust that propels the long fuselage rapidly along the runway. The aircraft gains speed steadily, and as it reaches the necessary velocity, the nose lifts off the ground smoothly. Moments later, the main landing gear also leaves the runway, and the aircraft becomes airborne. The B777-300 climbs gradually into the sky, with its flaps extended to provide additional lift during the initial phase. Once a safe altitude is achieved, the pilots retract the landing gear and flaps, adjusting the climb rate for a smooth ascent. The aircraft continues its departure, heading toward its assigned flight path. The water spray test, also known as the wet runway or water ingestion test, is a crucial certification procedure for commercial aircraft. The Airbus and MC21 jets undergo rigorous trials where they taxi or take off through specially prepared runways covered in water. These tests evaluate how the aircraft performs on wet surfaces and ensure that water does not get ingested into the engines or compromise braking systems. The Airbus aircraft generates impressive water plumes during high-speed passes, demonstrating its engine design and wheel splash protection. Similarly, the Russian MC21 performs repeated water runs to verify system resilience and safety under extreme wet conditions. Engineers monitor the tests closely, analyzing spray patterns, engine response, and system behavior. Passing this test is essential for flight certification, ensuring safety during operations in heavy rain or on flooded runways. The Airbus A350-1000 is the largest variant of the Airbus A350 family, an advanced wide-body twin-engine aircraft. Designed for long-haul efficiency and passenger comfort, it can carry up to 366 passengers in a standard 3-class layout, featuring 18-inch wide economy seats. Powered by Rolls-Royce Trent XWB engines, the A350-1000 offers a range of 16,100 kilometers. It measures 74 meters in length, with a top speed of 1,099 kilometers per hour and an optimal cruising speed of 903 kilometers per hour. The aircraft made its first flight on November 24, 2016, and continues to set new standards in fuel efficiency and passenger experience. Reut 360 is an innovative tire-building machine developed by Lucatech. For the first time, it integrates 3 stations into a single unit: the Reut extruder, a roller/stitching unit, and an automatic tread application table. Designed with a modular concept, the Reut 360 offers high productivity with fewer operators, reduced costs, and energy savings. Its compact layout allows flexible configuration according to production needs. Additionally, it features cloud connectivity and can be integrated with plant management software for optimized performance and monitoring. The Lucatech Reut 360 is a cutting-edge tire retreading machine that integrates 3 operations into a single, highly efficient unit. Developed by Lucatech, a company with over 18 years of experience in tire retreading innovation, the Reut Red 360 boosts productivity and ensures excellent process quality. It performs extrusion, rolling, and stitching simultaneously, significantly enhancing the speed and precision of the retreading process. Reformers who have invested in this technology are seeing outstanding results. The Reut Red 360 represents Lucatech's commitment to continuous improvement and high-performance solutions in the retreading industry. The TAAA-DHC-8Q400, operating flight DT-311 from Luanda to Huambo, lowered its landing gear and performed a smooth touchdown at NOV Airport on November 2, 2022, completing the short domestic flight safely and efficiently in Angola. Bahia. The aircraft accelerates down Udaipur's 2,743 meters asphalt runway, lifts gracefully above arid Rajasthan. Aircraft are enormous and powerful machines, with some weighing up to 400 tons and reaching very high speeds during takeoff and landing. Despite their size and complexity, their only point of contact with the ground is through their tires. These tires must withstand extreme forces, absorb heavy impact, and provide a safe and stable landing. Because of this, aircraft tires are carefully designed and manufactured to meet the most demanding performance and safety standards. Aircraft tires are built to handle enormous loads and high speeds, all while remaining relatively compact. Due to limited space in the landing gear compartment, designers must balance size, weight, and performance. The materials used in the construction include a combination of rubber, steel, fabric, and aramid fibers. Aramid is a synthetic material that is extremely resistant to heat and abrasion. It can withstand temperatures of up to 500 degrees Celsius, whereas untreated rubber starts to melt at around 260 degrees Celsius. Aramid is the same material used in firefighter suits and Formula One racing gear, providing high durability in extreme environments. Thanks to this reinforcement, aircraft tires can last through approximately 500 landings before needing to be replaced. A crucial part of the tire is the bead, made from braided steel wires coated in rubber. This component secures the tire to the rim and accounts for about 5% of the total tire weight. The tire must be strong enough to endure static loads between 22,000 to 30,000 kilograms and resist deformation at speeds exceeding 400 kilometers per hour. The manufacturing process begins with the precise placement of the tread, the outermost layer of the tire that makes contact with the runway. This process is guided by lasers to ensure perfect alignment. The tread is made from a specially formulated rubber compound designed to resist wear, cuts, and cracks. Once all layers are in place, the tire is pressed at high temperatures to bond the materials together securely. Every stage of the process involves detailed measurements and quality checks to ensure accuracy. After assembly, the tire enters the vulcanization phase. It is placed in a closed mold, and hot pressurized air is injected to push the tire walls against the mold's surface. This shapes the tire and strengthens its structure. After cooling, the mold is opened and the tire is removed and inspected for defects. Following manufacturing, the tire undergoes rigorous testing. It is tested for traction, acceleration, compression, and pressure resistance. Simulated landings are performed using specialized trucks that replicate the speed and weight of an aircraft during landing. Front and rear landing gear tests are also conducted to analyze the tire's stress performance. Once approved, the tire is mounted on an actual aircraft, such as the Airbus A350, which performs repeated takeoffs and landings, including on wet runways, to simulate real operating conditions. High-speed runway runs test its behavior under emergency landing situations. Aircraft tires are inflated to around 200 psi, much higher than car tires, which are around 32 psi. They are filled with nitrogen gas, which is more stable under temperature and pressure changes than normal air, ensuring safe performance at high altitudes. After passing all inspections, the tire is ready to take flight, supporting the giants of the skies with strength, precision, and reliability. The retraction test of the landing gear is a critical procedure conducted after the replacement of all landing gears on a Boeing 747. Since the aircraft's landing gears are vital for takeoff, landing, and ground movement, it is essential to verify their proper function before returning the aircraft to service. Eclease. To begin, jacking tests are performed. The entire aircraft is lifted using heavy-duty hydraulic jacks positioned under designated jack points. This setup simulates in-flight conditions by suspending the aircraft off the ground, allowing the landing gear to extend and retract freely without touching the ground. Due to limitations in the ground pneumatic system, which does not provide sufficient power to operate all gear systems simultaneously, the landing gears are tested individually or in pairs. This step-by-step approach ensures that each gear receives enough pressure and that its retraction and extension mechanisms function correctly. During the test, technicians command the gear to retract, as it would during a real flight. Each movement is closely monitored to check for abnormal sounds, delays, or hydraulic leaks. The gear is then extended back to its landing position, confirming that the system operates smoothly in both directions. This procedure is repeated for all landing gears, including the nose and main gears. Only after passing all retraction tests can the aircraft proceed to further checks or return to service, ensuring both safety and mechanical reliability. The entire process reflects the high standards of maintenance required for commercial aviation. The Boeing 787 tire replacement process involves several precise steps using specialized tools and equipment. First, heavy-duty jacks lift the aircraft to access the landing gear. Before removal, technicians inspect the tires for wear, damage, and pressure. The tire is deflated using a dedicated tool, and the axle nut is removed with specialized wrenches, similar to those used in motorsports. The wheel assembly is then carefully detached, often supported by a dolly. Next, the wheel and brake assembly is thoroughly inspected. If needed, the old tire is removed and replaced with a new or retreaded one. The wheel assembly is then reassembled and inspected again. Once complete, the aircraft is lowered, and final checks including torque and system tests are performed. Access panels are closed to complete the process. Because of high inflation pressures and safety concerns, wheel replacements are often done in specialized workshops, with entire wheel assemblies swapped instead of just the tire. The Boeing 767 landing gear wheel removal and installation, YouTube IDAO PTFB1_JB4, the mechanic follows a structured maintenance procedure. First, the aircraft is safely secured, and hydraulic or mechanical downlocks are applied to prevent gear retraction. Chocks are placed and the brake system is depressurized to ensure the wheels are safe to handle. Removal phase begins with loosening and removing the wheel retaining nut. The technician carefully pulls off the wheel assembly from the axle after ensuring the wheel spacer remains intact. Before discarding the wheel, a thorough inspection of the brake disc and hub area is conducted to check for wear or damage. Moving to installation, the wheel assembly is positioned onto the axle, making sure the spacer is seated correctly. The technician then torques the retaining nut to the precise specification required for bearing preload. It's critical not to loosen the nut to align bolt holes. Instead, torque must be reset to 0 and retorqued if alignment isn't achieved at full torque. After securing the nut and verifying lock bolt alignment, nitrogen is used to inflate the tire to the correct pressure to ensure proper support and balance. Throughout both phases, the maintenance crew uses safety pins, ground release tools, and alternate extension procedures to prevent accidental gear movement or door closure, as referenced in the ATA32 system documentation. The gear retraction test on the Airbus A330 is performed while the aircraft is raised on jacks, simulating flight conditions. This procedure allows engineers to observe the full operation of the landing gear system During the test, the main landing gears are retracted to evaluate the shortening mechanism, which helps reduce gear length for efficient storage within the fuselage. The test ensures proper synchronization, mechanical integrity, and hydraulic performance. By closely monitoring this retraction cycle, technicians verify that the system functions correctly and safely before the aircraft enters or returns to service. When maintenance crews swing the A319's main landing gear, they rotate each gear leg roughly 90 degrees into the service position. In its normal flight configuration, the twin-wheel main gear remains extended downward. Once the aircraft is jacked, the oleo-pneumatic shock absorber strut retracts, and the drag strut allows controlled rotation of the leg outward from its attachment point under the wing. Yachts at road. During this process, a fixed torque link ensures proper alignment of the wheels and prevents uncontrolled twisting. As the gear swings, hydraulic actuators inside the drag strut and associated folding strut release mechanical locks, allowing the gear assembly to pivot sideways. Technicians often rotate the gear manually or under light hydraulic assistance, observing the smooth articulation of both gear leg and associated doors that remain closed during swing. This swing exposes the gear bay for inspection and servicing, particularly for overhauling struts, checking hydraulic lines, and servicing proximity sensors and uplock assemblies. The swing rotation is typically performed when the aircraft is offload and fully secured, ensuring zero weight on the wheels so that the strut can telescope and rotate freely. It is a critical maintenance procedure that supports safe gear overhaul or inspection without fully retracting the gear into the wheel well. With the gear swung out, components such as the drag strut, UP locks, and wheel bearing hubs become accessible for maintenance detail. The TRM Eagle OTR63 performs a fully automated process that includes peeling, buffing, brushing, and grooving for large tires ranging from 20.5 R25 up to 59/80 R63. The process begins with peeling, where the outer layer of rubber is mechanically removed from the tire's surface. This eliminates worn or damaged material, creating a clean and even surface. The tire is precisely rotated while sharp cutting tools strip away the top layer, ensuring dimensional accuracy. Next is the buffing phase. A high-speed abrasive wheel smooths and textures the peeled surface to improve bonding conditions for potential retreading. This step ensures uniform rubber removal and consistent surface roughness, essential for structural integrity. After buffing, the machine performs sidewall brushing. Rotating wire brushes thoroughly clean the sidewalls, removing dirt, oxidation, and residues. This enhances both the tire's visual appearance and readiness for any additional treatments. Finally, the regrooving stage uses adjustable cutting blades to recreate tread grooves on the tire's surface. This restores traction and extends the tire's operational life. The system ensures each groove is formed at the correct depth and angle, optimizing performance for demanding off-road conditions. Throughout the process, the Eagle OTR63 operates automatically with precision control, minimizing manual intervention and ensuring repeatable results for high-volume tire refurbishment. The turnup bladder, specifically designed for tire assembly, manufactured by SNTA, this product supports tire sizes across a wide range and integrates seamlessly into modern tire building workflows. In operation, the bladder is positioned within the tire builder drum. It inflates uniformly, effectively rolling the ply cords up over the bead area. This ensures accurate ply alignment, firm bead seating, and optimal shaping of the upper sidewall. As the bladder expands, it applies consistent pressure, pushing the plies into position, which is critical for achieving a precise and smooth green tire build. SNTA's turnup bladder is built to fit both single-stage and dual-stage TBR tire building machines, offering flexibility across machine brands like VMI, Continental, and others. Its design prioritizes durability and performance consistency, ensuring reliable, repeatable results across runs. Overall, this bladder plays a pivotal role in enhancing tire uniformity, reducing defects, and supporting efficient production in TBR tire manufacturing. A highly efficient turnup bladder forming machine used in the production of radial truck and bus tires. TBR, this specialized machine is designed to mold inner bladder's flexible rubber components critical in shaping tire layers during the tire building process. The system operates by feeding pre-cut rubber sheets into a heated mold cavity. Once the mold is closed, heat and pressure are applied to shape the rubber into a precise bladder form. After a brief curing period, which takes less than 1 minute, the mold opens and the completed bladder is automatically ejected. The entire process is fully automated, ensuring consistent quality, high precision, and minimal cycle time. The machine's robust structure and fast turnaround make it ideal for high-volume tire manufacturing environments. Additionally, the use of mold heating and controlled pressure allows for accurate dimensioning and strong structural integrity of each bladder. This machine plays a vital role in modern tire production lines by enhancing productivity while reducing manual labor and manufacturing time. It exemplifies advanced rubber molding technology in the tire industry. The Bauer Model 8071 wheel assembly stand is designed to support the safe and efficient assembly of large and small aircraft wheels. In the video, the stand is shown handling large aircraft tires with ease, providing a stable and secure platform throughout the process. This robust equipment allows a single operator to mount and demount wheels without the need for additional assistance, increasing productivity while reducing manual handling risks. Its adjustable arms and rotating mechanism ensure proper alignment and accessibility during tire installation. The Model 8071 is ideal for heavy-duty maintenance operations, especially in aviation workshops where safety, precision, and ergonomics are critical. Overall, it streamlines wheel assembly tasks for various aircraft types with unmatched convenience. The production of a modern tire is a complex, highly engineered process that transforms raw materials into a durable and safe product used by millions of vehicles worldwide. This process involves multiple stages, including mixing, component preparation, building, curing, and inspection. The journey begins with rubber compounding. Natural rubber, synthetic rubber, carbon black, sulfur, oils, and other chemicals are combined in specific proportions. These materials are blended in large internal mixers under high heat and pressure to form a homogeneous rubber compound. Different formulations are used for various parts of the tire, such as the tread, sidewall, and inner liner. each requiring unique characteristics like flexibility, strength, or wear resistance. Once the rubber is prepared, it is processed into different components. The calendering process bonds rubber to fabric or steel cords to produce sheets used for body plies and belts. Meanwhile, extrusion machines form continuous strips of rubber that are cut into specific shapes for the tread, sidewalls, and other layers. Precision and consistency in thickness and dimensions are critical at this stage. Next comes tire building, where all the components are assembled. On a tire building machine, the inner liner is laid down first, followed by body plies, beads, sidewalls, steel belts, and the tread. These components are layered carefully and joined to form what is known as a green tire. At this point, the tire has its basic shape but lacks structural integrity. The green tire is then transferred to a curing press, where it undergoes vulcanization. A mold closes around the tire, while a bladder inflates inside it, pressing the tire against the mold. Heat around 175 to 180 degrees. Canned pressure cure the rubber and imprint the tread pattern and sidewall markings. Vulcanization transforms the rubber's properties, making it strong, elastic, and heat-resistant. After curing, the finished tire undergoes a strict inspection process. Each tire is checked visually for defects, measured for balance and uniformity, and in some cases, scanned using X-ray technology to ensure internal consistency. Only those that pass all tests are approved for use. This advanced process, as shown in the video, combines precision engineering, material science, and automated technology to produce tires that meet the demands of modern transportation, ensuring safety, comfort, and performance on every journey. In conclusion, tire manufacturing is a highly controlled process involving advanced machinery, skilled labor, and rigorous quality standards to ensure each tire performs reliably and safely under demanding road conditions.